Alright, so now we're going to move on to section 5.7, which is optimization. So remember when we did related rates and I told you that's one of the most important things that you need to get from this entire semester? Well, that's also going to be true about optimization. So this is something that is very important in the calculus world. Also, there are a lot of applications to optimization. So what does it mean for optimization? Well, we're trying to make something the best that it can be. So we're trying to, in this case with calculus, maximize or minimize things. You know, for instance, you want to minimize cost, or you want to maximize size for a given amount of material. So these are examples that we'll see for optimization. So again, very important. Alright, so here's a classic type of optimization problem. You have 40 feet of fence to enclose a rectangular garden along the side of a barn. What is the maximum area that you can enclose? So here's my picture. This right here is the barn. If I call this side X, I can call this side Y, and now I need to try to maximize the area. So let's first talk about the strategies for optimization, and then we'll come back to the problem. So when we're trying to maximize or minimize something, we first want to identify the variable to maximize or minimize. So in this case, we're trying to maximize the area. So then I need to come up with my area equation. So in this case, I know A equals X times Y. Okay, so now I want to write it in terms of one variable though. So what's the relationship I know between X and Y? Well, in this case, because I have 40 feet of fence, I know 40 equals 2X plus Y, and therefore I know 40 minus 2X equals Y. So now I can write this as A equals X times 40 minus 2X. So now I've written it in terms of one variable. And if I want, I can distribute this. Okay. So now next we want to find the first derivative and its critical values. So find the first derivative here. I know A prime is going to be 40 minus 4x. Find its critical values. So if I set this equal to 0, and if I solve this, we'll end up with so I get a critical value of 10. Well, now what? Well, I need to determine, is this a maximum or a minimum? So in order to do that, we can do the second derivative test, or we can do our increasing and decreasing chart for the first derivative. Here, because the second derivative is very, very simple, I'm going to do the second derivative test. So the second derivative is -4. So since then A double prime of 10 is less than 0, I know that this is going to be a maximum. So now we can finish our problem, and we can say, since A prime of 10 equals 0 and A double prime of 10 is less than 0 at x equals 10, is a relative max. So then we have to pay attention to, well, remember, what was the question actually asking us? It was asking us what is the maximum area. So now we need to find what is the maximum area. A different way, we could have the same problem, but it could say what are the dimensions for the maximum area. But in this case it's saying what is the maximum area, so then I want to find what is A of 10, and I can do 40 times 10 minus 2 times 10 squared, which is 200 feet squared. So now, since this was a word problem, we want to answer the problem in the context of the problem. So the maximum area that can be enclosed is 200 square feet. Now, another thing I want to point out that we have to check, because we're trying to maximize or minimize something, think about when we first learned about absolute maximums and absolute minimums. What about endpoints? And so we need to go back up here to the original equations that we had and think about what are the restrictions on x and y. And so in this case, I'm actually looking at this equation right here, or the combination of those equations. I know that y has to be between 0 and 40, but it's not including 0 or 40. And x has to be between 0 and 20, but not including 0 and not including 20. So because these are both open intervals, I don't have to worry about checking endpoints. But if these were closed intervals, I would have to also look at the endpoints to see, is one of those a maximum or a minimum? Or in this case, is it a larger maximum than 200 square feet? But since those are open intervals, I don't have to worry about that. Okay, so that's checking the endpoints of the domain. So again, the steps: identify the variable to maximize or minimize, write it in terms of one variable, find the derivative and its critical values, and then check the endpoints of the domain if necessary. So if the function that you want to optimize has more than one variable, use substitution to rewrite the function. That's what we did in this case by substituting in for y. If you are not sure that the extreme you found is a maximum or minimum, you have to check. It's going to be very rare that you would be sure that it's a maximum or minimum, so you're almost always going to have to check. So that's using the second derivative test or the increasing and decreasing chart. And if the endpoints could be the maximum or minimum, you have to check those as well. Okay, so now I want you to try example number 2. Which points on the graph of y equals x squared plus 1 are closest to the point 0, 2? I'll give you a hint if you're confused. Closest means distance. Okay, so pause the video, try to do that problem, unpause when you're ready to check your work. Alright, so we should end up with the points root 2 over 2, comma 3 halves, and negative root 2 over 2, comma 3 halves are closest to the point 0, 2. Now, how do we come up with that? Let's go back up here. So I drew a picture. It's going to look something like this, because I know that's what that quadratic looks like, and I'm looking for these points x, y, and negative xy. So then I did the distance formula. So I know d equals the square root of x minus 0 squared plus y minus 2 squared. Now remember, we need to get this in terms of one variable, so I know y equals x squared plus 1, so I substitute that in for y. So d is the square root of x minus 0 squared is just x squared, and then y became x squared plus 1, and then minus 2 squared. This simplifies to x squared minus 1. Now I multiply this out, and I end up with d equals the square root of x to the 4th minus x squared plus 1. Now here I have to recognize that d is going to be smallest when the function x to the 4th minus x squared plus 1 is smallest. So I don't need to take the derivative of d, I can just work with what's underneath the radical. So when I take the derivative of f of x equals x to the 4th minus x squared plus 1, I get f prime of x is 4x cubed minus 2x, set that equal to 0 to find my critical values, and I end up with x equals 0, and x equals plus or minus 1 over root 2 are my critical values. At this point, I didn't rationalize yet. I do make sure your answers are rationalized. I personally think it's easier to sometimes work with radicals when they're not rationalized as far as understanding how big or small the number is. It's just my personal opinion. If you want to rationalize at this point, you can, but you don't need to until the end. So now I chose to do an increasing decreasing chart. We could have done the second derivative test as well, but the second derivative test I believe is going to fail at the 0. Maybe not. Anyway, I did an increasing and decreasing chart. If you want the second derivative test, that's fine. And so I plugged in -1, -0.5, 0.5, and 1, and then I can see that -1 over root 2 and 1 over root 2 are minimums. 0 is a maximum. So then I write that down using derivative speak because we want to justify our answers. And now remember that the question asked me for what are the points on the graph. So I know the x values, but now I have to find the y values, and the y values are the same. So if I plug in root 2 over 2 or negative root 2 over 2 into the original function, either way I get 3/2. So then I answer my question in the context of the problem. Excellent. Alright, example 3. So I want you to pause the video, unpause when you're ready to check your work, find the dimensions for a 1 liter cylindrical can that will use the least amount of material. Oh, sorry, one other thing back to this problem. Notice that the domain of this function is all real numbers, and so therefore we don't have endpoints to check. Sorry, wanted to point that out. Now, go on, pause the video, unpause when you're ready to check it. Alright, so you should end up with r equals the cube root of 500 over pi centimeters, and h equals 1000 over pi times the quantity cube root of 500 over pi squared centimeters are the dimensions that will use the least amount of material. Don't worry about the fact that these numbers are not nice. Most of the time I'll actually just want you to round to 3 decimal places if the numbers are not nice, but you should know how to do the exact values as well. If there's something like this, I do not expect you to rationalize. Same with this. It doesn't matter. That's not the point of the problem. Okay, let's look at how we get this. Alright, so first we want to recognize that we're trying to minimize surface area, so we need to come up with our surface area equation for a cylinder. That is 2 times the quantity pi r squared, so the area of the bottom and the top, plus 2 pi r h, which is the lateral area. Also, I want to recognize that there are no endpoints. This is an open interval. It's very similar to problem number 1, so I don't need to worry about checking endpoints. Okay, well, what's the other relationship that I know? The other relationship I know is the volume. The volume is constant in this case, so volume is pi r squared h, and so that is 1000 pi r squared h. So I know h is 1000 over pi r squared. So I substitute that in for h here. I simplify a little bit, and I get my surface area equation is 2 pi r squared plus 2000 over r. Now I take the derivative. The derivative is 4 pi r minus 2000 over r squared. Remember, do not do the quotient rule with something like this. Now I rewrite the derivative so that I can see the rational equation. So I have 4 pi r cubed minus 2000 over r squared. So I set the numerator equal to 0, and I set the denominator equal to 0 to get my critical values. Now, obviously at this point I know r can't actually equal 0, but I still need to do this because remember it can affect the intervals if I'm doing my increasing and decreasing test. So I do need to recognize that that's a critical value, although I know that that can't be a possible answer. So I do my increasing decreasing test. I see that this doesn't come out to be anything, but I see that I get a minimum here, so I use my derivative speak. The derivative is less than 0 on 0 to the cube root of 500 over pi. The derivative is greater than 0 on the interval cube root of 500 over pi to infinity. Therefore, at that value is a relative minimum. Plug that back into this equation to find that h value. Again, don't worry about simplifying that. And then write your answer in the context of the problem. Don't forget units for your answer as well. Okay, so there's one more problem to do. Obviously we're running out of time on this part, so we'll go on to part 2 to do that last problem. So you can go ahead and do that last problem and then open up part 2 to see the solution.